Hello. So today I want to talk about reference frames. We've reviewed now vectors and the calculus of vectors and how vectors can be used to describe physical quantities about a system that are vector quantities like position, velocities, accelerations, whatnot. Those all originate from having, there's some point P here that I want to identify. I have to establish, and I want to say something about position, I have to establish a coordinate system that has some sort of origin, some axes, ideally perpendicular axes, and then I can, in the case of position, write a vector that goes from the origin to that location, and that tells me the position of the object in that reference frame, in that coordinate system. So if I'm this person here, person 1, this is how I could identify the location of this particle. But suppose you, person 2, are over to the right. You also can identify the position of that particle, but it would not be the same position from your coordinate system. If you had your axis laid out with an origin located here, you might then say that the position of this particle is this vector that points from your origin to the particle. I might say the particle is up and to the right. You might say it's a little up, but more to the left. These are two obviously correct ways of describing the position of this particle. For each of them is correct for that given reference frame, for that given coordinate system. Now, if we all agree upon the coordinate system we're going to use, we don't have to worry about there being discrepancies between vector quantities in our coordinate systems. However, we might want to make sure that we have a way of communicating this information to each other if we are using different coordinate systems. Or I might ask, relative to me, I see the position as what? Given that I know my friend is way over there, what is the position of the particle relative to them? So this is what I will call translational relative motion that we're going to learn how to transform between two coordinate systems that are located via a translation from one to the other. So translational relative motion, we'll call that converting between coordinate systems that are simply translations of each other. And by translation, it just means that I'm moving the thing up and down, left and right, backward and forward. I'm not rotating at all. That will be the second half of today, where I might want to rotate the coordinate systems. So in this case, what I call x here is going to be pointing in the same direction as what you call x here. What I'm calling y, you also agree on the same direction for y. The axes themselves are oriented always the same, but the location, the origin, has shifted for these two coordinate systems. The good news is that it's essentially just vectors. If you can understand this in terms of vectors, it's very easy to compute relative motion based on vectors, which can be, I'm going to do this all in 2D. Obviously, this extends to as many dimensions as you want. So let's take the two vectors I have on the screen. So I have person 1, person 2, they're each looking at the particle. I could write down for their given coordinate system, from their given origin, I can write this vector, r, but I'm going to write it as r of p relative to 1. So this notation that I'm introducing, p divided by 1, is location of p relative to frame 1. Again, meaning that the arrow is just emerging from the origin of frame 1. So then this red vector is going to be r of p relative to frame 2, the position of that particle as seen from someone with the origin, their axes, given by frame 2 there. The thing that we need to complete this is the relative component between the two is some vector that connects the two. How are these axes oriented relative to one another? So this blue vector I'll call r of 2 relative to 1. The position of the entire second reference frame relative to as seen from coordinate 1 or origin 1. And if you look at this, notice I have, it's just vector addition. It looks like r of p over 1 is the same thing as if I take the vector r of 2 over 1 and then add to it r of p over 2. So it's really just vector addition. If I have a vector, the blue vector, that connects the two reference frames, I can translate between the position of p relative to 1 and the position relative to 2 just by a very, very simple vector sum. So for example, if I'm told if r of p relative to 1 is, say, 2 comma 2, and r of 2 over 1, whereas the second coordinate frame relative to the first is, let's call it 5 comma 1, then the position of the particle p relative to frame 2 is just going to be, by vector subtraction in this case, the position of p relative to 1 minus this relative displacement. So that looks like it's going to be 2 minus 5 comma 2 minus 1, or negative 3 comma 1. And if we look at the picture, that kind of makes sense. The person in frame 2 says that I have to go 3 spots left and 1 spot up to get to p, compared to the person in frame 1 who says you have to go 2 spots to the right and 2 spots up to get to p. That blue vector, the relative vector between the two reference frames, connects the two. So pretty easy. And then this works again with motion as well. If r of p over 1 equals r of p over 2 plus 2 over 1, then I could easily take the derivative of this expression. And if I call the derivative position velocity, that says the velocity of the particle as seen from 1 is the same as the velocity of p as seen from 2 plus the relative motion of the two reference frames. Maybe person 1 is standing on the ground, maybe person 2 is in a train that is moving to the right at a constant speed. That train, v of 2 comma, or 2-1, would be kind of the relative motion between the two frames. And then, anything else? No. Then, similarly, I could also say accelerations are related the same too. I could just take the derivative again, which could be helpful. And this is very helpful if you want to then try to understand, say, the motion of this apple as I throw it into the air. While I'm anchored to the ground, when I throw it up into the air, I, anchored to the ground, actually move a little bit because the Earth has rotated a little bit. So if I wanted to compute why, if I throw this apple high and high and higher and higher and higher, assuming there's nothing in the way, eventually I could throw it so high that it would actually end up falling next to me rather than falling directly back down into my hand. Because the Earth has rotated a little bit. There's an acceleration associated with that. That's one of the kind of, we might get a little bit, we might do that a little bit later on, but it's usually a second semester topic of that sort of stuff. Well, let's take a simple train example. E.g., if the particle is at 2, what did I say above? 2, 2. As viewed from person 1. Who is stationary, while person 2 is on a train that starts at person 1 and moves at a constant speed. Or constant velocity, rather. Let's call it 3t, 0. So the two reference frames are on top of one another at t equals 0. And then as time goes on, one of them is moving to the right in this case. And you could ask yourself, what is, if this is just velocity, let's call this just 3, 0. I skipped a step. I went to positions. And the question could be, what is, say, the position, velocity, acceleration of particle P as viewed from a person on the train? So let's draw a picture first. Here's person 1, looking at this particle P. And then there's a reference frame 2. So we'll call this as the origin of 1, it's the origin of 2. There's someone in the second frame, which is the train. Well, this is the ground. And again, the idea is that they start kind of on top of one another, then as time goes on, this frame is moving at a constant velocity to the right. I'll just leave it here. And then the question is, this position is how the ground person observes this point. And we want to say something about what is this vector as a function of time. Now we can do this, again, if we have this kind of connecting relative vector for the positions between the two reference frames. Now this blue vector here, the position of 2 relative to 1, if it starts at the same position as origin 1 and then moves only to the right, it is what I accidentally wrote down before, 3, t divided by 0. If it's moving at a constant velocity, which I just made up and said it was 3. The position of the particle relative to the non-moving frame, I said, is 2, 2. And then it looks like then that implies that the position of P relative to 2 is going to be R of P relative to 1 minus R of 2 relative to 1 in this case. Did I make a mistake up here? No, I did not. Okay, I did subtract. And that seems pretty straightforward. Given these two vectors, it looks like then it's going to be 2 minus 3t, and then 2 minus 0, or just 2. So the position, again, when t is 0, is 2, 2. Then as t gets bigger, it gets more and more, the x-coordinate gets more and more negative. I have to look more and more to the left from the train, right? Thinking if I'm standing on the train, the particle looks like it's moving to the left, even though the train is moving to the right. But you can now be a little bit more specific. The train is moving to the right relative to person 1, who's grounded on the ground. It's all relative. The velocity of, I'll stick with red, the velocity of particle 2 then is the derivative of these two vectors. Well, the position is a constant, and then that's minus, and then this just becomes 3 comma 0. So then the velocity looks like it becomes negative 3 comma 0. The particle from the train, p-2, from the train, the particle is moving to the left at a constant speed, while the train is moving to the right at a constant speed. But viewed from the train, the particle then is moving to the left. Accelerations, since we've gotten to everything as a constant, there's no acceleration in this case. Derivative of negative 3 is 0. So it turns out this would be, they could both apply Newton's laws of motion and they would get the same answer in this case, but I get ahead of myself. Now what if it was more complicated? Well, then who cares, right? It's all the same sort of thing, right? I have, call this the ground, and there's someone watching from the ground, and there's some tree on the ground, say, and they're observing a bird. Well, they would then say that here is the position of the bird relative to the ground. And then maybe there's a train. That's someone sitting down looking out the window of the train. So they're stationary relative to the train. They might say that, right, they could have some observation and there's some connection between the train relative to the ground. But then maybe you get up to go to the cafe cart and you're now walking along the train at some speed. So you're walking along the axis, in the coordinate system of the train, but you're moving with some speed. So again, then there's relative to, say, the origin of the train, which might be the back end of the train, say. Right? Maybe this is the position of, I don't know, what should I call this person? I guess I could use P, right? The person relative to the train. And then that person as they walk, that person as they walk could look out the window and observe a bird. And then that would be bird relative to person. So there's relative motion between the train and the ground. That's the first blue. R of t-g. There's relative motion between this person walking on the train relative to the train, p-t. And then they could compute the position of the bird as seen from them. And the expression they would have to write down is that the bird relative to the ground seems to be, by vector addition, the same thing as the train relative to the ground plus the person relative to the train plus the bird relative to the person. So if I knew these relative vectors here, and I knew the position as viewed from the person on the ground, I could then compute what the bird is doing relative to the person who is moving on the moving train. So it's really vector addition, which emphasizes that if you can write down a coordinate system with axes and an origin, you can move to any other coordinate system you want just by drawing vectors. It's all really just vectors. How my page was. All right. I don't know what happened. Now let's consider rotational motion, or rotational transformations. We're going to stick with the same origin, but I'm going to rotate the direction of the axes. So perhaps this is one of my origins, or one of my axes, which has an x direction, a y direction, and an origin. And there's some point that I want to investigate. Maybe I'll put it here. It has some y value and some x value, such that the position I could write down for that was a terrible arrow. The position I could write down for that point might be something like x in the x hat direction, y in the y hat direction. But then someone else could come and say, well, I want actually to have my axes oriented this way. Maybe the black line's oriented relative to, say, the horizontal tabletop and then vertical from the tabletop. But then someone else on a slant or slept funny and they're looking at everything kind of at an angle. They want to make the axes kind of, parallel and perpendicular in this direction. So that's fine. But then they might say that the x direction it points in that direction. So it's not the same. X hat and x hat dash are not the same. And then the y-axis points in that direction. And it is the same origin, but it is rotated by some angle, theta. Now in this case, they would have a very similar looking position vector that emerges from the same origin and points to the point. It's an identical vector actually. But in terms of coordinates, right, coordinate-wise, there's some x hat value here, and then some y hat value here. Rather than saying the position is x and y, it would be x hat, or x dot and y dash, or x dash and y dash. So then the position vector they would write down might be something like x hat, I keep saying hat, x dot, in the x direction, their x direction, and then y dash in the their y direction. And now the question is, if I knew the position x and y according to the black axes, and I knew that I was rotating the axis by a certain degree, theta, how can I then compute the positions x and y in the red axes, which notice are different? It looks like, going from black to red, the value of going from x to x dot gets larger, while the value of going from y to y dot gets smaller when you translate from the black values to the red values. So in this case, we have rotated the coordinate system. So what do we know? We know that this position vector, x in the x direction, y in the y direction according to the black, is actually the same as this position vector, which is according to their coordinate axes. So there is an equality there that can be helpful. And what we're going to do is we're going to, knowing what we know about the dot product, project the position vector r onto the new axes x hat dot and y hat dot. So I'm taking a vector and I'm going to figure out the components of that vector that are parallel to x hat dash and y hat dash. It's a projection. Well, that sounds a lot like a dot product. And indeed, that's how we can figure this out. So I know that x, the new x component, the part is going to be the part of the original vector that is parallel to x hat dash, right? Because remember, that dot product is saying what component of the position vector r is parallel to x hat dash. Well, this, I can also know what a dot product is. I know that r is x hat plus y hat. And then this is being dotted with x hat dash. So by properties of the dot product, it looks like this is just x times the dot product of x hat dot x hat dash, that's the first term, plus y hat dot x hat dash. I really just distributed the dot product, and then I am dotting the unit vectors. I can do the same thing for y, which is then going to be the position vector dotted with the y hat dash. Then this ends up being y x hat y hat dash plus, oops, sorry, that should be an x, and then the dot product of x hat and y hat dash, and then y with y hat dash. So given x and y, again, there's lots of x's and y's here. So remember, x and y with no decorations, that's the actual coordinates in the black axes. 2, 1. It would be the 2 and the 1. The x hat and the y hat are the directions of the x and y directions for the black axes. X hat dash, y hat dash are the directions of the x and y axes for the red. Could have given them different names, but I think you see the picture here. I'm going to write this in matrix notation. So what I want is to know what this new vector is, right? This vector of the new positions that point along the new x and the new y, the red x and the red y. Now if I look at the right-hand side here, it looks like I'm involving a product of x and y, but then there are these kind of 4 different dot products that happen. So I'm going to write it like this, and pause after I write this down to make sure you see how what is written on the upper right translates to this. So I'm going to write this as a 2 by 2 matrix where this coordinate is this dot product, this coordinate is the next dot product, and then same thing underneath for the y's. I'm going to write that not as a column vector, but as a thing that has two rows and 2 columns. And this is x, y, the original vector. So this is kind of the new vector r, r dash. This is the original vector. And then this is a 2 by 2 matrix, which I'm going to call M with 2 lines underneath. Since it's going to correspond to a particular angle too, I'll say that it's ultimately, we'll see, is going to be a function of theta. That theta value, again, being what is defined by how much the axes have rotated. So this M is a rotation matrix, ultimately, at the end of the day. It is a matrix that when I apply it to the original position R, will rotate the axes and give you back the coordinates and the new axes at the end of the day. Now, matrices, there's a lot of theory that you can go into when you take a linear algebra course. So let me just give the simple picture here of how do you do a matrix multiplication like this. Well, notice if you look at the lines directly above the matrix, to figure out the component x dash, it looks like I take this value and multiply it by x, and then I add to it this value that I multiply by y. So I took the top row and then went down the column vector here of this times this, then add to it this times this. So and then y then looks like it's this multiplied by x, then I add to it this multiplied by y. So they themselves kind of look like dot products. So given a square matrix M of theta, what does square mean? Where the number of rows equals the number of columns, in this case 2 by 2. If this were a 3D rotation, you could probably intuit that it would be a 3 by 3. And also we require that this equals the number of dimensions. or the size of the vector r. R has two elements, x and y. The matrix M has, each dimension has two, or there are two rows and two columns. Then if I want to write this down mathematically, the r sub I component of the new vector, I will even put a dash for this component. All right, so x hat might be r sub 1. Not hat. X dash might be r sub 1. Y dash might be r sub 2. Right? This might be the first component. This might be the second component, with the subscript 1, subscript 2. Is the dot product of the ith row of M with the original vector R. So an individual component of the new vector is a dot product of one of the rows of the matrix with the original vector. And again, notice if we go up here, this first entry, we might say r dash sub 1, is I take the top row, the first row, and that has two entries, and I compute the dot product with this vector, which then again becomes this times this, and then I add to it this times this. The second entry of the new vector is the dot product of the second row of the matrix with the original vector, which then gives you this times this plus this times this. That's all this is doing. And as it gives you a more compact way of writing down all these complex operations that it's happening on the single vector r, and you apply this matrix transformation. This is kind of a specific example of a more general set of things that you would do in a linear algebra class, or tensors, which is kind of the extension beyond vectors, where you can have tensor quantities for physical quantities, which are just matrices. So that's the machinery. I still need to evaluate what the heck all these dot products are. And again, presumably it connects in some way to theta, how I've rotated the two axes. So I need to compute what these dot products are. But that is actually not too bad. If I redraw, let me just redraw the axes. So I have the black axis, and then I've rotated it with the same origin to get the red by some angle theta. And again, this is x hat, y hat dash, and then this is y hat, x hat. So one of the first ones, it looks like it's x hat dot x hat dash. Well, these are two unit vectors, so their magnitude is 1. And I know that the dot product is the product of the magnitudes times the cosine of the angle between the two vectors. Is it theta? Is it always theta? Well, we have to be careful. In this case, it is theta. Because if I look, I can see that I have a unit vector that is pointing in this direction. That's x. I have a unit vector that is pointing in this direction. That's x hat dash. And the angle between those two vectors is indeed theta. So this is then cosine of theta when I evaluate the dot product. All right, all well and good. But what about y dotted with x dash? Well, in this case, we still have the x dash, so I'll keep that. But now the vectors we're looking at is this unit vector and the other unit vector here. So the angle between them in this case is not theta, but it's whatever this phi is here. So if I define that as phi, this looks like it's going to be cosine of phi. But this looks like it's just 90 degrees minus theta in that case. Which, if you think about it, it sounds like there's going to be a trig identity there. And indeed, this just ends up becoming sine of theta. All right, next. Original x, but now the y dash direction. So now let's get rid of these. So now it looks like I'm talking about, I'll just use blue, this direction and this vector. In which case the angle seems to be not theta, not phi, but this thing here, whatever that is. Well, that looks like it's going to be cosine of, it's at least 90 degrees. And then it's not too hard to then realize that this is also theta if I rotate the axes. So this looks like it's cosine of theta plus 2 plus theta. Which, is that a trig identity? You bet. Negative sign. Then finally, y hat dotted with y hat dash. That looks like it's instead this angle, which in that case is just theta again. So this looks like it's just cosine of theta. So when I write down the transformation is this matrix times the original vector, it looks like m in this case, m as a function of theta, is the 2 by 2 matrix that is cosine, sine, negative sine, cosine. If I tell you a theta, that uniquely determines these 4 entries, which you can then apply to the original vector to get the coordinates that it resides in if you were to shift the axes. Right, so again, it's good to remember that this is shifting the axes by theta. So let's, of course, do an example. Let's do one where I kind of can intuitively visualize it as well to make sure that when I do this, I get something that sounds sensible. So let's take the point 1, 0 and rotate the axes by 90 degrees, counterclockwise. So let's draw it first. Here's the point at 1, 0. Then imagine if I take that and I rotate it 90 degrees, the axes are then going to be something like this, where this is y, the positive y direction, and this is the positive x direction. Again, just think of rotating the axes. In that case, if I look at just the red axis, so block out the black and just imagine the red axes were drawn, you can tilt your head. Seems like the point is located now at, I would say, 0 in the x direction, the red x direction, and then -1 in the red y direction. Let's see if that works out. So I have the new values, x dash and y dash, is going to be this matrix. So cosine of 90 degrees is 0, sine of 90 degrees is 1, negative sine of 90 degrees is -1, cosine of 90 degrees is 0. Applied to the new the original coordinate 1, 0. So then if I were to evaluate this matrix multiplication, I first take the dot product of this with this. So it looks like I have 0 times 1 plus 1 times 0. That looks like it's just 0. And then I have the second coordinate is the second row dotted with this vector. So it looks like it's -1 times 1, added to it 0 times 0. So then that looks like it's -1. Indeed, that's kind of what I intuitively assumed the answer would end up being. So again, this is you've rotated the axes and transformed the location of that coordinate relative to this new frame of reference. Someone in this case who has really slept funny and is walking around with their head tilted a full 90 degrees. You can both be standing in the same spot, you have the same origin, but you still agree on different positions for that particle in this case. And again, if maybe it's rotating, maybe you're standing on a merry-go-round, and so you can treat that as your coordinate axis is rotating maybe at a constant speed. In that case, the value of theta might be a function of time, right? And you can multiply this out and come up with some sort of expression that is a function of time for the position of a particle, say. Now I'll end just with a quick aside, is that sometimes what you want to do is maybe I have a particle here, P, and rather than rotate the axes, I want to stick with the same axes, but I just want to rotate everything inside the axes. So rather than rotating the axes by theta, it might be that you want to rotate the point by theta, where this angle here is theta. So I'm keeping the same axes. Maybe I want to always have the same axes, but I still want to have that rotation. So in that case, I'm rotating everything kind of inside the axes. So here you're rotating the point by theta instead of rotating the axes. What is the new position compared to the old position? It again can be thought of as just a matrix, and it turns out it's almost exactly the same matrix, but you just use negative theta instead. And I'll let you reason that out on your own. You can also, this one actually is much easier to prove because you can write out the positions of R and R dash much easier and show that it really is, again, a rotation, and you can use the same rotation matrix, but just use negative theta instead. If you want to stick with the rotation matrix that's above. So, or if you want to just remember what this matrix is using trig identities, right? This first entry would be cosine of negative theta. But cosine is an even function, so it turns out that that is the same thing as just cosine of theta. It doesn't change. So then this cosine of theta doesn't change. But then sine of negative theta is the same thing as negative sine of theta. So then this becomes negative sine of theta. And then here the negatives cancel and it becomes sine of theta. But again, I would just be careful to remember, because if you look at these two, if I were to highlight one, right, we spent a lot of time building up this one, but that's, again, shifting the axes by theta. Where if you remember this one, notice the negative sign is in a different spot. They look almost identical, except the negative sign is in a different spot. You just have to remember that this is, you're rotating everything inside while keeping the axes the same. All right, so, and it turns out that any kind of general any sort of general motion can be decomposed. We won't worry too much about this, but you can take any kind of arbitrary motion and break it up into a combination of translations, moving things around, and rotations, right? So you could have perhaps a train that's moving, but then if the train takes a bend, right, you might have a rotation that's associated with that as well. You can write that down if you want to as a combination of translations and rotations, and still have a way to agree on the position of, say, a particle or a bird or something as things move around. All right, very good.